Good morning. So I want to start talking about chapter 6. So we're going to be discussing, we're moving sort of from the more mechanistic part of the course to a more synthetic part of the course. As I said, this course in a way parallels some of the various advanced areas that get covered in more depth in graduate courses. And we're coming in at a level that's definitely above the sophomore level, where you're being asked to remember and still understand all your mechanistic thinking that you've learned in sophomore organic chemistry, functional groups, stereochemistry, but then to build on that. And so in the next 3 chapters, we're going to be building on synthetic organic chemistry. And where we're going to start out is talking about functional groups. So we'll spend 3 lectures on functional group transformations and get maybe a little bit more of a sophisticated angle than one gets in sophomore chemistry. I think for me, a unifying theme that runs through my thinking about functional groups and functional group transformations is the concept of oxidation state. It's something that, I think almost even just under the surface, without even thinking about it, I am pigeonholing functional groups into certain oxidation states and then understanding their interconversions as having no net change in oxidation state, like a hydration reaction, or having a net change in oxidation state, like an oxidation or reduction. It's a good way to put things into a framework. So let me show you what I mean. So moving sort of from high oxidation state to low oxidation state, we'll start with carboxylic acids, and we can go all the way down to alkanes. So in other words, the carboxylic acids, and I guess what I'd call this is sort of, obviously there are zillions of functional groups, but what I'd talk about is sort of our major functional group classes. So the carboxylic acid family envelops carboxylic acids, acid chlorides, esters, amides, nitriles as well. And they really all go together as a group. If we move down an oxidation state, we get the ketone and aldehyde family. And so I'm talking ketones, aldehydes, but also acetals, imines. If you want to go a little further afield, although you start to move across carbons, you get to enols and enamines. But let's just, so basically you can sort of say enamines are sort of the byproduct of imines, same family. Enols are the byproduct or same family as ketones. Moving down a level, we come to the alcohol family. And so for alcohols, I'm talking alcohols themselves, but also ethers. The OR group of esters, alkyl halides, all of these go together. Amines, the amide NR2 group, the R groups on the amide. And then if we want to think a little further afield, we can talk thiols, the sulfur analogs of alcohols, and thiol esters. And that would be the SR group of them. And if we continue our traipse down the levels of oxidation state, we come to alkynes, alkenes, and alkanes. And I don't know, I mean, to me, this is sort of the bulk of things. And yet, for the sake of completion, I think I want to bring in sort of two other families and maybe develop this idea of oxidation state. So carbon dioxide is fully oxidized carbon. It's +4. Oxidation state. The carbon dioxide family includes important compounds. You've got carbonates. So basically, carbonates are the diesters of carbonic acid. It's an important functional group. It may well be one of the ones that's closest to you. It might be right under your rear ends. Plastics, many plastics are polycarbonate. My glasses are polycarbonate plastic. So it's not a trivial functional group. You don't encounter them as much. Carbamates, or let's say carbamates would be another. The nitrogen analog, the amide analog, your protecting groups, your Bach protecting group, and so forth. I'm just going to write that as NR2 there. Chloroformates, the acid chloride analogs. I could go on with more example. That's a chlorine here written very curly, very scripty. I could go on further, but maybe I'll just add one more member that sort of fits right in as the parent of a lot of these. Phosgene. Phosgene is the double acid chloride of carbonic acid. It is a deadly, deadly gas. It was used in World War I to gas people. It's also a very useful reagent in the laboratory to form, for example, chloroformates and other members of the carbon dioxide functional group class. I guess if I want to be maybe completist, I'll also mention methane at the other end of the oxidation state, not really a family, but carbon dioxide and methane sort of make a nice starting point for reviewing this whole concept of oxidation state. So remember the idea of oxidation state. The idea is it's a formalism. It's an accounting mechanism, but it is a very useful accounting mechanism. Who remembers it from freshman chemistry? The basic idea is if you're dealing with covalent bonds, like in carbon dioxide, you play a little game. Covalent bonds involve the sharing of electrons. But in terms of accounting an oxidation state, and we'll see how this is useful as we develop the idea of oxidation state in today's lecture, in the purpose of oxidation, of formalism, of accounting, you say even though the bonds are covalent, they're polar covalent. In other words, they're not share equally, they're share unequally. We're going to treat the bonds as ionic bonds and give the electrons to the more electronegative element. So in carbon dioxide, oxygen is more electronegative. Its Pauling electronegativity is 3.4. Carbon has an electronegativity of 2.5. It's more electropositive. So we're going to say, all right, we're going to, for the purposes of bookkeeping, for the purposes of this formalism of oxidation state, we're going to give those electrons to oxygen and take them away from carbon. Now, carbon brings to the table a nuclear charge, unbalanced, of +4. In other words, if you strip carbon of its electrons, right, it wants 4 electrons. A carbon atom has 4 valence electrons, and of course 2 1s electrons, which we're not counting, so 6 electrons total. But your 4 valence electrons, if you take them away, you're left with a charge of +4. In other words, +4 minus 0 electrons is +4 oxidation state. The oxygen, conversely, has +6 as its nuclear charge. In other words, it has 6 valence electrons in a neutral oxygen atom. So +6 is the unbalanced nuclear charge. We have in our formalism given 8, so our net is -2. And oxygen is generally -2 oxidation state. Except in peroxides and the like. For methane, and this is why I say the opposite end of the spectrum, for methane, hydrogen is more electropositive than carbon. Hydrogen has appalling electronegativity of 2.2. And so if you again play this sort of game, this sort of formalism, and you say, all right, we're going to do this, but now since hydrogen is more electropositive, we will go ahead and have hydrogen give up its electrons. We give those electrons to carbon in this formalism of oxidation state, in this bookkeeping of oxidation state. And so our carbon now has +4 from the nuclear charge. In other words, 4 unbalanced positive charges for the valence. It wants to have 4 electrons in a carbon atom. But we have -8. Our oxidation state is -4. That makes sense. You go ahead, you burn methane, right? If you light your gas stove, you burn methane. You are fully increasing its oxidation state. You are oxidizing methane. You are oxidizing the carbon to carbon dioxide. Thoughts? Comments? Yeah.
So this just has to do with like the electronegativity of...
Yeah, it's a formalism. So the question is, does this have to do with electronegativity? It's basically, okay, we understand the atoms in a covalent bond are sharing the electrons. But in terms of accounting of who, quote unquote, owns those electrons, if we have to give them totally, we give them to the more electronegative element. It is and we're going to develop this idea as we traipse through oxidation states and see how useful this is. So basically, this is a very useful concept for keeping track of types of reactions. Yeah, other.
This is just of like the central atom?
It's going to, we'll use it at the reacting center. So for example, in ethane, we assign oxidation state in the same way, and the one wrinkle in the rule is that when carbon is bound to carbon, we share and share alike. So rather than giving both electrons to one carbon or both to the other, we give 1 and 1. And so in ethane, our oxidation state, instead of being -4, is -3 for carbon. All right, let's see other questions. These are good questions. This is sort of the base of things. Yeah.
You always look at one carbon at a time when we do that?
We do, and so the question is, do we always look at one carbon at a time? we do look at one carbon at a time. What you're going to see is when we do the sum and total, we'll see if there's a change. So let's say in a moment, we're going to look at the reaction of an alkene to an alcohol or an alkyne to a ketone, and we're going to look at the two carbons that are involved in the reaction.
I know this is like a little bit off of organic chemistry, but what about for like like inorganic?
You can do the same for metals. You can do the same thing, and indeed we do. When we're dealing with, say, chromium, we can apply. We'll talk probably next lecture about some chromate oxidations, and we'll see chromium go from +6 to +4 as we go from chromic acid to chromous acid. And this change of two oxidation state is a common theme, where most organic reactions go in twos. In other words, oxidation states go up or go down in twos as you go through a reaction. Most oxidizing agents in organic chemistry are two-electron oxidizing agents and change oxidation state by two, at least initially. So chromium oxidation, the chromium goes from +6 to +4. Permanganate oxidation, the manganese goes from +7 to +5. And that also helps you balance your stoichiometry, because ultimately, say in a permanganate oxidation, your manganese is going to +4, which allows you to say, okay, if I'm going to move up two oxidation state units for an organic compound, and I'm carrying out a manganese oxidation where my ultimate product is going from KMnO4 to MnO2, 3 oxidation state changes, you can readily balance your redox chemistry saying, okay, that means I'm going to have 3 organic molecules, each changing oxidation state by 2, and 2 permanganates, each changing oxidation state by 3. So it's a very quick way to understand stoichiometry for redox reactions. Other questions?
How would you assign oxidation states to carbonates with 3 oxygens?
Carbonates, exact same as carbon dioxide, which is one of the reasons why immediately I'm seeing this all in the same family. Remember, this bond to oxygen is a double bond. All those electrons go to oxygen. These bonds to OR groups are single bonds. The electrons go to oxygen. We're left with carbon in the +4 oxidation state. So immediately I see a carbonate, a carbamate, and a chloroformate. I think of them all together in the same oxidation state. The other thing that's permeating my thinking is that all of these, just as acid chlorides, are all functional groups of acid chlorides, esters, etc., all belong to the carboxylic acid family. These all belong to the carbonic acid family. Carbonic acid is not a stable entity that you can put in the bottle, which is why when you lose H2O, you get carbon dioxide, which is why I said we're going to call this the carbon dioxide family, but it is, carbonic, formally a carbonic acid family. Other thoughts, other questions? All right, let's start to look at where we're pigeonholing things. So, okay, carboxylic acids +3 oxidation state, ketones +2, aldehydes. I just grouped them all in together. So basically, I'm writing on the same level because I'm grouping things together. This has to do with the difference in electronegativity of carbon, and carbon being the same, carbon and hydrogen being different. So aldehydes +1. But what's very useful, look at this functional group. What's this functional group called here? What do we call? Acetal. This is an acetal. And it's specifically, as I've drawn it, an acetal of a ketone. You apply the same thinking and you say, oh wait, that's +2 oxidation state. obviously that goes with a ketone. Or you go ahead and say, all right, this acetal and aldehyde acetal is +1 oxidation state. No change in oxidation state in going from an aldehyde to an acetal, or a ketone to an acetal. How do you make an acetal? How do you synthesize an acetal from an aldehyde? Alcohol and acid catalyst. Typical no oxidation state change reaction. Now we come over here and we say, all right, let's go ahead and look at an alcohol, right? So alcohols we know are related to aldehydes. Alcohols are related to ketones. So what's the oxidation state of the carbon I'm pointing at? What's the oxidation state of the carbon bearing the aldehyde?
+1.
-1. How do you get -1?
Each of the protons are going to be times +1. The other carbon, so our group is neutral. You have a -1 for the alcohol. Bring it together, you have a -1 for the carbon.
Exactly. And so immediately you can see that if you're thinking about moving between an aldehyde and an alcohol, you're talking about a reduction reaction. Or conversely, if you're talking about moving between alcohol and an aldehyde, you're talking about an oxidation reaction. But if you're talking about, say, moving between an aldehyde and the corresponding acetal, you're not talking about oxidation or reduction. And then when you're thinking about the chemicals, the reagents that carry out these reactions, immediately you're saying, well, of course I use a reducing agent like sodium borohydride to convert an aldehyde to an alcohol. Of course I use an oxidizing agent like PCC to take a primary alcohol up to an aldehyde. And it all sort of starts to fit in. And as I said, by the vagaries of electronegativity, then because we're dealing differently with carbon, if we're talking over here for a secondary alcohol where we are, for a secondary alcohol, we are, at 0, right? Because you count the carbon as not having an effect, you count the hydrogen as making -1, you count the oxygen as making +1, so -1, +1 cancels out, you get 0. You follow?
Yeah. But don't you mean the other way around, though? You said alcohol is +1.
Alcohol,
I mean, like the alcohol functional group.
oh, yeah, you go ahead, you take the electron, you go ahead, you say, all right, we go ahead, we give these electrons, we take these electrons, we share these electrons equally, and so we get 0, right? Plus, we get +4 for the carbon, -4 equals 0. And for a tertiary alcohol, for our bookkeeping on a tertiary alcohol, what do you do on that?
All the carbons are going to be neutral relative to the central carbon. The alcohol is going to be -1. It's going to be +1.
+1. All right. So, as I said, this is something that just sits as an undercurrent in my thinking about functional group reactions. Let's move on to some actual functional group interconversions and traipse among families and between families. All right, so the the oddest looking member of the carboxylic acid family is maybe the nitrile, right? And I said it's in the carboxylic acid family. If you do the same formalism, it's +3. Or carbon triple bond nitrogen, that's a lousy nitrogen. And so you look at the conversion to, say, a carboxylic acid, and as I said, this concept of families, this concept of oxidation state family should just be embedded in you. You look at this change, this functional group interconversion from a nitrile to a carboxylic acid, and you say, oh, no net change in oxidation state. This is something that occurs by a reaction that only involves water, only involves no change in oxidation. In other words, this is a hydrolysis reaction. And indeed, if you want to take a nitrile and convert it to a carboxylic acid, you just cook it up with acid or with base. So if I wanted to write this generically, I'd say RCN goes to H3O plus, goes to RCOOH. Now if I go to the stockroom and I say, give me a bottle of H3O plus, they're going to look at me. You can't just put H3O plus in a bottle, right? That's always some aqueous acid. So that's like a shorthand for aqueous sulfuric acid or aqueous hydrochloric acid. So if I go to the stockroom and I want an acid to convert my nitrile to a carboxylic acid, I better say, hey, can you give me a bottle of sulfuric acid? If I have benzonitrile, I can go ahead and cook up with aqueous sulfuric acid and heat. I can go ahead and cook up my benzonitrile, and I get benzoic acid. Nitriles are a little bit slow to hydrolyze, so this occurs with some heating. You need a little bit of energy to make that reaction go. I am not going to write a curved arrow mechanism for this reaction. You should be able to write a curved arrow mechanism for it. If you're rusty on this, go back to your sophomore organic chemistry text. Sebastian and Stan have promised to have some curved arrow mechanism workshops for us to boost up our skills and all the things we've gotten rusty on over the past couple of years. All right. With very little discrimination among conditions here, I'll just write out one more condition for a hydrolysis. Acid and base are sort of useful in general for hydrolysis conditions. I'll just show one related reaction. We could go ahead and say, take an ester and treat it with, say, NaOH in H2O, followed by a workup where we say add HCl, aqueous HCl. And we would hydrolyze. I started with methyl dodecanoate, at least if I counted correctly, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so just as a related example, I could go ahead and say hydrolyze an ester to an alcohol and the corresponding carboxylic acid. I could use acid, I could use base for either of these reactions. All right, so by way of contrast, let's go ahead and start with our carboxylic acid. But now let's go ahead and say we want to go to a primary alcohol, right? And here we clearly are changing oxidation state, right? Our carboxylic acid family is +3. Our primary alcohols are -1. And so we can say, oh, okay, this is a reduction. We're dropping the oxidation state. We need a reducing And of course, I'm talking more than just carboxylic acids. I'm talking about the whole gosh darn family, esters, lactones, the whole bloody thing. And what's interesting about this is you also are looking and saying, oh, wait a second, there's a net change of -4. In other words, it's not just a reduction, but it is basically moving 2 notches, not 1 notch. Notches go in pairs. In other words, we're not moving to the +1 oxidation state. We are moving to the -1 oxidation state. There's an oxidation state in between. That's the aldehyde oxidation state. And so immediately embedded in my thinking becomes the idea, oh, maybe there are reducing agents that could stop me at the aldehyde oxidation state. In the case of carboxylic acids themselves, it's pretty hard. In the case of esters and particularly lactones, dibal is a reducing agent that often can take you down just stopping at the aldehyde oxidation state. Your textbook gives lots and lots of examples. What I'm trying to do here is show big overarching principles. All right, so coming back to this specific example, let's say we want to go down. My go-to reducing agent, the thing that will reduce every carbonyl functional group down, every carboxylic acid, every ester, every nitrile, every aldehyde, every ketone, is lithium aluminum hydride. It is a bull of a reducing agent. It is a powerful reducing agent. It is soluble in ethereal solvents. Solubility is important. Solubility makes the difference in a lot of chemistry. Sodium hydride also has hydride in it. Sodium hydride acts as a base, and it acts as a base usually with a proton transfer, sometimes through a little bit of alcohol. It's not a reducing agent. But that solubility of lithium aluminum hydride, sodium hydride doesn't dissolve in just about anything, that solubility of lithium aluminum hydride in ethereal solvents allows it to interact intimately with the molecules. The aluminum doesn't hurt either. So lithium aluminum hydride, LiAlH4, can deliver up to 4 hydrides in the reduction process. LAH and THF are an ether, followed by an aqueous workup, which I'm going to tell you about in just a second, gives rise to the corresponding alcohol. This is proline over here. L-proline is an amino acid. We've made the corresponding alcohol called prolinol. Lithium aluminum hydride can be a real pain in the neck to work up the reactions because the aluminum salts get to be gelatinous. And so people have worked out conditions. Either you want to precipitate them out with some base, or you want to, and water, or you want to dissolve the aluminum salts with some acid. You can do either type of workup. In this particular case, we're generating an amine. And so if I added acid, no doubt I'm going to want to isolate my product by liquid-liquid extraction, right, in a separatory funnel. If If I added acid, I'd be generating the ammonium salt, amines are basic, and then my product would go into the aqueous phase. If I want my product to go into the organic phase, I better use a basic workup. KOH and H2O are good conditions. There are also some conditions that are basically neutral with water and sodium sulfate. Now, as we move beyond the sophomore level, one of the things you want to think about is that all of the chemistries that you do are things that you can actually do in the laboratory. And often you ask yourself, if you're in a research lab, like Sebastian and Stan are, you ask yourself, how do you go ahead and actually do this reaction? Technically, what do I need to do this reaction on a new substrate? One of my favorite go-to places is the compendium Organic Syntheses, sometimes called OrgSynth. Organic syntheses are well-optimized chemical procedures that have been tested by other people so they're reproducible, usually using minimal volumes of solvent and so forth, and they are great models. This particular example I took from Organic Syntheses, volume 65, page 173. On your journals page, on your chemical literature page, I have links to OrgSyn and to other useful sources like JOC. When you do the homework and you want to read more about the problems, and there are some interesting problems in this week's homework set that are taken out of OrgSyn and taken out of JOC, you can go ahead and click on those links and read about it. Here's another example, again from OrgSyn, and I'll just show you this with an acidic workup. So in this case, if I use the same reagent, if I use my go-to lithium aluminum hydride, in this case, the OrgSyn prep does it in ether, and then I do an aqueous workup with sulfuric acid, H2SO4, and water, now I get the corresponding chloroalcohol. This was done with a single enantiomer, and so one of the nice things is that you can preserve your stereochemistry here. Here's a good example where you wouldn't want to use a base workup. If I use a base workup, I might deprotonate this oxygen and get intramolecular reaction, intramolecular SN2 to form an epoxide. Much better to use an acidic workup. And this particular example references from OrgSynth, volume 66, page 160. Often carboxylic acids are harder to carry out reactions on than esters because carboxylic acids can be deprotonated. So if I add a Grignard reagent to an ester, it adds very easily. If I add a Grignard reagent to a carboxylic acid, not so easily because it deprotonates to form the carboxylic acid. Some reagents, on the other hand, are selective for carboxylic acids, and I think the concept of selectivity is pretty cool, so I want to show you one example where we put an ester and an alcohol in competition. Diborane, or BH3, often available, often used as a solution in THF, followed by an aqueous workup, selectively reduces the carboxylic acid without touching the ester. I think that's sort of cool, but it's useful also because it helps express this concept of selectivity. You get essentially boron coordinating or forming a borate ester and then transferring hydride intramolecularly. You can also do this with sodium borohydride and iodine as another way of generating borane in situ. I'll say NaBH4 plus I2. We don't have time to talk about all the different reducing agents, but I'd like to list some. I mentioned dibal. It's a lousy B. Sometimes you'll hear it dibal, sometimes you'll hear it dibal H. NaBH4, sodium borohydride, hydrogen with palladium on carbon. All of these are milder than lithium aluminum hydride. Sodium cyanoborohydride is especially mild because of the electron withdrawing cyano group. That's often just good for iminium ions. So I'll say milder. And at least for these guys, they do not reduce carboxylic acids or esters. All right, I am going to now switch from oxidation reactions and talk about reduction reactions and talk about reactions that don't involve a change in oxidation state. Let's look at this hydration reaction. Yeah?
Quick question. So, if you're using BH3 and THF, how would you actually make that solution? Would you just bubble the BH3 through?
So you could indeed bubble it through THF. One of the things that's really, the question was, do you just bubble BH3 through THF? So one of the things that's really advanced synthetic organic chemistry is that many reagents that are difficult to handle are now available in solution in bottles. So borane is a pyrophoric gas. B2H6 is in equilibrium with BH3, borane, diborane. Borane is a pyrophoric, but diborane is a pyrophoric gas, very hard to handle, catches fire and air, but BH3 and THF is available as a solution. And here, if I use sodium borohydride and iodine, I'm also generating diborane in situ, so it's another way of generating. But yeah, it's a pain. Gases are a pain to work with. Solutions in general can be syringed safely.
So how does the iodine, make the sodium borohydride not attack the esters?
So esters, as I said, sodium borohydride is mild enough that it doesn't reduce esters under typical conditions. And the iodine and borane react sodium borohydride react very rapidly to produce diborane. So it's an in situ way of generating it. Nice reaction. One way you handle a solution by syringe, the other way you handle solids that are, relatively easy to handle. All right, I want to move on to this reaction here. Our oxidation state of the central carbon is 0. Our oxidation state of the terminal carbon is -2, right? We have 2 hydrogens attached to it, so that's -2, and then 2 carbons, so that's no additional contribution. Now you come to your tertiary alcohol, and you'd say, wait a second, we've changed oxidation state. At that carbon, we're +1. But we've also changed oxidation state at this carbon, we're -3. In other words, we have no net change in oxidation state. It's the same net oxidation state. And so it makes sense that just like our interconversion of a nitrile to a carboxylic acid, where it's a hydration reaction or a hydrolysis reaction, It's exactly the same sort of situation over here. In other words, all we're doing is adding water across the double bond. You go ahead, you say take aqueous sulfuric acid, and you can convert a tertiary alkene to an alcohol. And you should be able to write a mechanism for that reaction. You protonate the alkene to generate a tertiary carbocation, water attacks, you lose a proton from the hydronium ion, from the water, from the protonated alcohol. All right, let's continue to traipse through this concept of oxidation state. Tertiary carbocations form with relative ease. This reaction doesn't occur without some heating, but it occurs. Secondary carbocations are much harder to form, and furthermore are very prone to rearrangements. So particularly when we're dealing with secondary alcohol formation, oxymercuration reduction is a very good reaction because the mercury tames the carbocation and facilitates its formation and prevents rearrangement. Now, reduction's a funny word here because I just said in converting an alcohol or an alkene to an alcohol, there's no net change in oxidation state. And if you brush off your sophomore organic chemistry notes and remember what this reaction means, we're taking mercuric acetate or another mercury 2 salt in the first step with water. We're going ahead and in the next step adding sodium borohydride. The overall result is we go and we get the alcohol. The reaction proceeds by way of a cyclic mercurinium ion. I'm not going to go ahead and write all of the mechanism here, but we go ahead. We have a mercury. We get a carbocation that gets special stabilization. Water attacks, and I'm shorthanding everything. We lose a proton. And then the mercury is reduced off. And what's actually changing oxidation state in this reaction is the mercury. The mercury, we are going from mercury +2 to mercury 0, which is in part what allows us to break the carbon-mercury bond. But the carbon, we have no net change in oxidation state. Now this is whether acid-catalyzed hydration or oxymercuration. This is what you call Marovnikov addition. Organic chemists love control, and we love to be able to choose how a reaction goes. You can get what's called Antimarkovnikov addition. In other words, the opposite of the natural regioselectivity by hydroboration, oxidation And so if we take our same alkene, I've just written it as a generic alkene, and we treat it with BH3 and THF or 9BBN or whatever our favorite boron source is, and then alkaline hydrogen peroxide, now we go to the corresponding primary alcohol. In other words, we get the opposite regiochemical course of the reaction. The reaction goes by way of hydroboration, and then I'll just draw this with two squiggly bonds here because you can add 3 equivalents of boron across the double bond, and then oxidation of the carbon-boron bond. All right, so last reaction that doesn't involve a net change in oxidation state that I want to show you is just the hydration of an alkyne. And so we'll take a look at a terminal alkyne like so. And when we go ahead and we treat, and I'll tell you about the catalyst in just a second, when we treat with water and a catalyst, a mercury catalyst, we get a ketone. And if you look at this chemistry, again, 0, -1, +2, -3, no net change in oxidation state. Mercury salts of various forms are a good catalyst for this reaction for the same reason that mercury promotes oxymercuration reduction. So again, borrowing from org-syn for some conditions, sulfuric acid, water, and just a catalytic amount of mercuric oxide, HgO, gives rise to the corresponding ketone. And I'll just cite my references. This is Org-Synth Collective Volume 5, 4, page 13. You can work out the mechanism. Once again, your mercury 2 acts like a fat proton. You protonate, you basically add mercury, water attacks, you go through some ketol-enol tautomerizations, you lose Hg+, that gets you to an enol, and then you tautomerize to the ketone. Overall reaction, catalytic in mercury, and no net change in oxidation state. We will pick up talking about some oxidation reactions next time.